All right, I think we're ready to get started. So, bonjour et bienvenue. My name is Erin Hales, and I'm so excited to be here with you all in Paris. So today I'm going to be talking about optics and the journey of a cross-chain message. Let's see. Okay, mind if we back up? Anyway, so yes, today we'll be talking about optics and the journey of a cross-chain message. I show you this picture. This is a picture of me 3 years ago. It was the beginning of two things for me. The first is it's the beginning of me working in the cross-chain interoperability space. And the second, it's the beginning of me working with the best hair in crypto. Jokes aside, at this time, cross-chain was not really a thing. At least not in the trustless, non-custodial way that the crypto gods intended. We were working on a Bitcoin relay, and we launched the world's first cross-chain auction. Over the next 2 years, we saw a lot of growth in the cross-chain space, and we began collaborating with other people that were interested in interoperability. However, we still had a long ways to go to achieve the vision that we had in our heads. We have seen a lot of growth in the space. However, we also see a few problems. The existing systems are costly. Message flow is unidirectional, and adding a new chain is difficult and time-consuming. Additionally, we are seeing the rapid development of new systems. This causes further fragmentation and increases the demand for bridges. When every solution must be a completely bespoke design, it will become increasingly difficult to meet that demand. So I'd like to introduce optics, which stands for Optimistic Interchain Communication System. So what is optics? I'm glad you asked. Optics is an interoperability standard for building cross-chain communication channels. Optics itself is actually not a bridge. Rather, it lays the foundation upon which we can build bridges. These cross-chain applications are called apps. Zaps. Stands for, it's spelled X apps, and it's pronounced zaps. The developers can leverage the underlying channels to build and write software that executes on multiple chains. Unlike other bridge designs, optics has a one-to-many solution. This enables chains to enter a rich ecosystem of communication. Messages can be sent bidirectionally and to any number of other chains. Additionally, optics has fewer contracts, so it is significantly cheaper. It is also trustless and non-custodial, and adding a new chain into the system is easy. This benefits the blockchain community as a whole and allows chains to benefit from the strengths of other chains. For example, increased user base, low transaction fees, carbon neutrality, and shorter block confirmation times. So here is the different components of optics, and we're going to be covering how it works. Many of you are new to optics, so this is going to be an excellent introduction into how it works and why it's important. We'll begin with the home. The home is the center of optics. It is an on-chain contract responsible for confirming messages and putting them into a message tree and maintaining a queue of tree roots. It also holds the updater bond, which we'll talk about later, and can slash that bond if the updater misbehaves. The replica. The replica is the on-chain contract responsible for replicating the message route on some other chain. Optics differs from other bridging solutions in that it has a one-to-many relationship. The home chain can be connected to any number of other replica chains. Additionally, this structure allows for fewer contract deploys. So as I mentioned earlier, that makes it significantly cheaper. The replica is also responsible for maintaining a queue of pending updates, validating message proofs, and dispatching messages to other destinations. The replica does not have visibility into the state of the home contract. So for that reason, we have the updater. The updater attests to updates. So it pulls the home contract for new routes and then signs an old route, new route pair and returns that to the home. It is possible for an updater to produce a fraudulent update. However, it's very easy to detect when this happens. So we will see if that happens, and we have in place the proper measures to handle that. The watcher observes the home and observes the updater's behavior through the home. This is how we detect if there has been a fraudulent update. The watcher can easily see if a signed update is not correct, and so it notifies the home and also notifies each of the replicas. The home can then slash the updater, and the replicas can respond accordingly. And then both need to be restarted with a new updater. We ensure that fraud is very costly, so there's little to no incentive for any fraud to occur. The relayer pulls home for new updates and forwards them on to the replica. It also pulls the replica for confirmable updates that have passed their time and confirms them and updates the replica's route. The processor's job is to generate and submit Merkle proofs for pending messages and then dispatch those proven messages to the recipients. The processor does maintain a local Merkle tree as well as a list of messages and their corresponding leaves. So here's the journey in a perfect world of how a message would be processed. So the happy path. The home prepares a message by adding the necessary information, the origin, destination, and sequence info. Then the home contract inserts that into the message tree and logs the message. The updater, it pulls the home and produces the signed update and sends that to the home. The relayer then relays that message onto each of the replicas. The replicas confirm that update, and then the processor triggers the message processing, and it is sent on to the replica on another chain. So this all happens behind the scenes, and yeah, your message is processed. In the world that we live in, it's not perfect, so obviously we have accounted for the sad path, which is when a fraudulent update occurs. There are two cases, an invalid update and a double update. If both of these are fraudulent, you may ask why we handle them separately, and that's an excellent question. The double update is something that we can detect on any chain, and so since this is easily detected, we've decided to take the strong defense against it. So as a double update occurs, It is similar to the beginning of the last slide, except the updater produces the double update and tries to send it directly to the replica. The watcher is watching the home and the replicas, and it pulls them for new updates. And when it sees this, it like checks that update, sees that it's fraudulent, and notifies the home and the replicas. The home and the replicas verify that this is fraudulent. The updater is slashed, and the replica responds, and then both are halted and must restart with a new updater. The other case is an improper update, which is where the updater signs a fraudulent update. Let's see. So this is where it tries to send a faulty update to the home, which is very easily detected. The watcher sees that, and it notifies home, and again, home slashes the updater. Well, home verifies that it's fraud first, and then it slashes the updater, and again, both of them restart with a new updater. So that is how a message is processed. If you join us again later, we have some talks that will cover how you can build a cross-chain application on top of the system. So thank you all for your time.